Imagine this, you flick on a torch in a dark room, and instantly the light seems to fill the space. But even light, as fast as it is, has a measurable speed, and it's the fastest thing we know in the universe. In a perfect vacuum, light travels at about 3 times 10 to the power 8 meters per second, more precisely 299,792,458 meters per second. In air, its speed is almost the same as in vacuum. But the moment it enters any other transparent medium, like water or glass, it slows down. This slowing of light is the main reason why refraction happens, the bending of its path when crossing from one medium to another. And here's something important, the speed depends entirely on the optical properties of the medium, not just on how heavy or dense it is. To measure how much a medium slows down light, scientists use the Absolute Refractive Index, often just called refractive index. We define it as the ratio of the speed of light in vacuum to the speed of light in that medium. The formula is n equals c divided by v, where c is the speed of light in vacuum and v is the speed in the medium. Since v is always less than c for any transparent material, the refractive index is always greater than 1. For example, glass has a refractive index of 1.5. That means light moves 1.5 times faster in air than it does in glass. Let's compare some real numbers. In water, light travels at about 2.25 times 10 to the power 8 meters per second, giving a refractive index of 1.33. In glass, it drops to around 2.0 times 10 to the power 8 meters per second, that's why n equals 1.5. Diamond? That's a real slowdown for light. With n equal to 2.41, light creeps through it, which is one reason diamonds sparkle so much. Remember, optical density is not the same as material density. For example, kerosene floats on water because it's less dense physically, yet it can be optically denser. Sometimes we compare how fast light travels in one medium directly to another without involving vacuum. That's when we use the Relative Refractive Index, denoted nu12. The formula is nu12 equals v1 divided by v2, where v1 and v2 are the speeds of light in the two media. We can also write it as nu12 equals n2 divided by n1 using the absolute refractive indices. Example, between water, n equals 1.33 and glass, n equals 1.5, nu of water with respect to glass is 1.125. That means light is 1.125 times faster in water than in glass. So what actually changes when light moves into a new medium? Three main things. First, the speed changes. It decreases from rarer to denser medium and increases from denser to rarer medium. Second, the direction changes unless the incidence angle is zero, which is why light bends in refraction. Third, the wavelength changes because speed changes, but the frequency stays exactly the same. Frequency depends only on the light source. In air, we can write C equals F times lambda, where F is frequency and lambda is wavelength. In a medium, V equals F times lambda prime. The frequency is unchanged, so the shorter the wavelength, the slower the light moves. Now, why does light's speed change differently in different situations? Three main factors. 1. The nature of the medium. Higher optical density means slower speed and higher refractive index. 2. Temperature. Increase the temperature and the speed of light in the medium increases slightly, lowering its refractive index. 3. Color or wavelength of light. In air or vacuum, all colors travel at the same speed. But in glass or water, red light travels faster than violet light. That's why the refractive index for violet is higher than for red. This wavelength dependence is the reason for dispersion when white light spreads into a rainbow in a prisma. Let's work through an example. Problem: the refractive index of a liquid is 1.36. Find the speed of light in it. Step 1. Write the formula N equals C divided by V. Step 2. Rearrange V equals C divided by N. Step 3. Substitute V equals 3 times 10 to the power 8 divided by 1.36. Step 4. Calculate V is approximately 2.205 times 10 to the power 8 meters per second. So, in this liquid, light moves at about 220 million meters per second. Alright students, let's quickly wrap up the key points about the speed of light. First, the maximum speed of light in vacuum is C equals 3 times 10 to the 8 meters per second. Nothing in the universe is faster. But in any other medium, like air, water, or glass, light slows down. Next, we have the Absolute Refractive Index, denoted as N. It is calculated as N equals C divided by V, the speed of light in that medium, and it's always greater than 1. Then, when comparing to media, we use the Relative Refractive Index, nu12, which is the speed in medium 1 divided by the speed in medium 2. You can also express it as N2 over N1, the ratio of their absolute refractive indices. Remember, the wavelength changes as light enters the new medium, lambda prime equals V divided by F, but the frequency stays the same, so the color doesn't change. Finally, light's speed is affected by factors like the optical density of the medium, temperature, and even the wavelength, which causes dispersion, like the splitting of colors in a prisma.